So we can move on to the next presentation by Gabriela.
Yes, hi, Professor. Let me just share my screen. Are you seeing my screen now?
Yes, with your slides, the other slides.
So I have to run it, right?
Yeah.
Is that okay now?
Yeah, fine. I think this will run. You've got some videos in there, haven't you?
Yes.
Okay.
We can see two pages actually there.
Yeah, for some reason it's running because but it's showing you the next page.
Yeah.
Also,
you may want to say duplicate.
This one?
Yeah, that's fine.
That's good. That's good.
That's the one? Okay.
Okay, you can start.
Okay, good morning, everyone. My name is Gabriela Gallegos. I'm a research fellow at London's Advanced Innovation Centre in Cambridge. I'm going to present today the safe inspection of reinforced concrete structures by an autonomous robot called SIRCAUR. This is the outline of my talk. I will start with a brief introduction and the objectives of my research. The development of the adhesion module, in which I will concentrate most of this talk. Next, the development of the robot structure, some experimental results, and finally conclusions and acknowledgement. So the objectives of the research, the aim was to actually develop a lightweight autonomous mobile robot that can climb on reinforced concrete structures, surfaces to deploy a precision non-contact GPR sensor to detect river corrosion and other related defects. It will help on reducing cost of inspection by eliminating scaffolding or upsealing access cost. It also will improve the safety of the inspector and increase productivity. The operational environment are RC structures with around 30 to 35 millimeters of concrete cover, such as high-rise buildings, so bridges, dams, car parks, lofts, etc. Obviously, can you see my mouth? Yes. My mouth.
Yes.
Obviously, this kind of environment will be ideal, where we have a lot of ferrous structures, but we will also research on different type of structures like columns and foundations. Furthermore, it carries a camera for visual inspection and detection of concrete cover deterioration. It works autonomously on the ultra-wideband control trajectories, which are adjustable by GPR sensor feedback to avoid poor river regions. It also transmits all the NDT data to a ground-based CPU for processing. When designing climbing robots for industrial applications, the operating environment and sorry, I lost my mouth. The operating environment and the tasks to be carried out are the main factors to take into consideration when designing a climbing robot. So regarding the locomotion system, it could be wheeled, legged, tracked, or frame type robot. Research activities on wall climbing robot has been carried out for several years now. But when it comes to non-ferrous surfaces, the adhesion system tend to employ either energy-intensive suction, dynamic vortex, or adhesion methods. But when it comes to ferrous structures, the preferred choice is either permanent magnets or electromagnetic adhesion. While the electromagnets offer the ability to control the magnetic adhesion on command, they require constant energy consumption to maintain the magnetic field. So the payload capacity, mobility, adhesion, safety, and energy consumption are the main feature that we look for. But regarding the engineering, the difficulty on engineering a climbing robot for reinforced concrete structures still remains a challenge. Regarding the adhesion module, we design what we call a magnetic flux design toolbox to try to achieve the maximum adhesion force while keeping the adhesion module weight at the minimum. We use COMSOL Multiphysik to develop this app. It's actually kind of an app to help us on the optimization process. It is actually really easy to use. It kind of looked like this. I'm still losing my mouse. Well, it has several features. You can change the size of the magnet or the yoke or the ferrous surface geometry really easily. You can vary the spacing of the air gap, or in what we call the concrete gap. You can use pre-geometry button to see your design and the computer study to run the study. From our previous research, it has been proven that the best configuration to achieve the maximum adhesion force is using 3 magnets with an north-south-north orientation on an iron yoke. So basically, these are the parameters that we need to take into consideration when designing our adhesion module. The magnetic adhesion system that we designed was simulated over 12 millimeter steel rebar, while varying the concrete cover from 100 millimeters to 1000 millimeters. We use N52 neodymium magnets with the size of 50 by 50 by 25 thickness. The distance between the magnet was said to be at 50 millimeters, so the length of the magnet actually, and the iron yoke was only 10 millimeter thickness. So this is how we look our simulation. This is how the flux magnetic lines look like when we have a 50 millimeters concrete gap and when we have a 10 millimeters concrete gap. So we could see that the closer to the river, the better the adhesion force that we have. As an example, the resulting adhesion force computed at 30 millimeters was 142.1 Newton, which is more or less 14.6 kilograms or pull force. To validate these simulations, we construct our adhesion model, taking into consideration carefully measuring the magnet distance. So we use these plastic spacers. We also check for the polarity of the magnets, and the final layout that we came up for testing looks something like this. The weight of this whole adhesion module was around 2.8 kilograms. Then we went to our instrument machine at TWI facilities to validate the simulation and run the test rig. So we have here the magnets, and we started at a distance around 200 millimeters, I think, from that we actually slowly close the gap to be around 25 millimeters to the rebar, while gathering all the information on this computer. We can actually see by the spacers, which are the same size of the magnets, that we achieve 25 millimeters to the river. So we have a little video here where we can see the experiment, and the graph compares the experimental results and the FEA results, demonstrating a good agreement. However, we can see around 5% error that was recorded when the air gap was around 30 millimeters, and the minimum error was recorded when the air gap was around 40 millimeters. We can think that this was due to a systematic error. Nevertheless, the experimental results provides evidence to validate the simulation results. as now we have proven that our simulation was correct, we start designing our adhesion module with different configurations. We started just with 3 magnets and start adding more magnets in order to achieve the best also behavior of the robot, if I may say so. We vary different river meshes, different spacing of the rivers to see how we can also achieve the best adhesion force. We finally come up with this 9 magnets layout with 50 millimeters spacing between them. And we build our test rig that looks like this, where we add some load cells to be able to record also the adhesion force. And we set it up with an aluminum channel to keep them together. In order to test it on a real wall and to test all these different simulations, we also design a dynamic wall where we can change the rivers, I mean the diameter of the rivers and also the spacing in between the mesh, the different rivers. This is how it looks, our experiment. So I'm gonna just show you the 100 by 100 river spacing. Here we can see that we checked also for different positions of the test rig, either angular or horizontal. Horizontal means that it will follow exactly the river. As for the development of the robot structure, we use this, we based the construction of this robot on this adhesion module. Sorry. Oh, so the features that we have are the entity module will be located here. Here are the magnetic adhesion module, and here is the rebar position detector. Also, all the electronics were here with the camera and the wireless communication with the controller. All this structure was made of fiber carbon, which is lightweight, plus aluminum for stiffness. For the localization model, we use an out-of-the-shelf ultra-wideband model due to the accuracy and the application feasibility, which means it can work with complex geometries. And during the design phase, the software for localization was developed and tested using an Arduino on an Amiga bot. Here's how it looks, our Arduino bot. And we actually were able to build ROS node to incorporate it easily on the robot software structure. For the GPR module testing, we use the Pico GPR, which is a geophysical device designed for subsurface sensing and monitoring of opaque materials such as ice, snow, pavement, soil, etc. This device enabled the calculation of the thickness of the layers inside such materials. Also detects and position different inhomogeneities within the material. We can see here the specification table of this device. But basically, we choose it because it's actually lightweight as well. To test for the sensitivity trials at TWR designed and constructed a concrete wall with known defects in it and within the embedded rivers. So we follow in 3 different sequences to detect these defects. The first one, for 8 void detection, the GPR was moved in the direction of 1 to 3, A to B, and 2 to 4, as it's shown in picture A. These paths were selected to avoid the rivers and to pass over the various different voids within the concrete block. The second sequence for river detection, the GPR was moved in the direction of 1 to A and to 2, and 3 to B and to 4. These paths were selected so as to avoid the voids to pass over the various different rivers to detect the defects introduced. The last sequence for river and void detection, the GPR was moved in the direction of 3 to B to 4, and then from 4 to B to 3. And the purpose of this trial was to evaluate the GPR with tightly spaced defects. This is how it looked, the result that we obtained from this device. The result in the first, in figure A and B, indicate that at 17 millimeters and 100 millimeters depth, all voids were detected. At a depth of 150 millimeters, only the 30 millimeters height voids were detected. The 20 millimeter height void was barely detected, and the 10 millimeters height void was not detected. The result on picture C indicate that the GPR detects all of the rivers in the sky paths. The downward trend of the peaks indicate that the rivers are positioned at increasing depths. Although the GPR detected all the rivers, it was incapable of detecting the reduction in the river diameters. In the last picture, we found that the GPR interacted with both the air voids and the rivers.
Can you conclude now, Gabriela?
Yeah, this is just a video. Can you see it running or not? Yes. So this is the vertical. And this is the horizontal climbing. This last one was to prove that the adhesion model was able to carry the payload of the robot. So as the conclusion, the aim of the project was to introduce a lightweight and fast moving with no use of any lifting equipment to climb on reinforced concrete in structures to inspect different defects. The entire structure of the robots was built in aluminum alloy and carbon fiber. We use N52 neodymium magnets for the adhesion module. We were able to detect rivers and defects and locate the robot using the ultra-wideband localization. So we can just conclude that our approach for a crawler-based robot was successful. So I just want to thank my partners, Innotech UK and TWI, and Innovate UK for the grant for this project.
Okay, thank you. Any questions? I've given you 3 extra minutes, so remember this favor in future. Any questions?
Thank you, Professor.
You're welcome. Any questions?
If I may be permitted another one, it's Clive Lopkin here again. Yeah, Gabriela, many thanks. Very interesting presentation.
Thank you.
In your system, you use the robot to scan the GPR over the concrete surface. What I'm wondering is whether you'd considered, instead of having the robot scan the GPR, whether you would have a robot that included an area of XY scanning so that the robot could position itself and then you could scan within, let's say, a square meter area by moving the GPR in an XY system. It's just a sort of a different approach, and I didn't know if you'd considered that and what the advantages or disadvantages would be.
Yeah, did you mean like pre-established trajectories?
Sorry?
Did you mean like pre-settled trajectories on X, Y, Z, so it can follow this?
I'm thinking that instead of having the robot that carries the GPR, that you basically have a frame that is moved around to various sections of the concrete structure.
Oh, okay.
And then an XY scanning system that moves the GPR within, let's say, a square meter area. I don't know if I'm probably not explaining it at all well, but
See, I think I understand the question. I think you're, instead of using a crawler, using just like a frame,
Yes.
XY, model, right? Yeah, I think it will work. The idea of using the crawler is also to test these localization trajectories. And for example, the robot was able to detect poor region rebars. So it will avoid this region, if you want to say it. You know what I mean?
The problem is not that. The problem is to get access to very large structures. So if you want to inspect a dam, you know, you have, let's say, 90-meter tall dam. You need to access different parts of that dam. So you need a robot to get you there. That's the main problem. If you include some kind of a scanner to cover a larger area, you'll just have to carry more load, essentially. And this method is already probably at its limits in terms of adhesion, because you've got a big air gap. So I must terminate here now because we are running late.